Hello, my name is Charlie. I am in the Bio 515 course this spring, and today I will be discussing with you the action potential process. So what is action potential? This is the process in which a message travels across a membrane within a neuron. And when I say message, that's a colloquial term. Of course, it's not literally a message, but a stimulus has caused a change within the cell, and the action potential is what is going to translate that message, so to speak. As we can see here, there are different phases of the action potential. In a normal cell without any stimulus, we call this the resting potential or the resting membrane potential. This is around -70 millivolts and is what, again, is non-stimulated. We have a threshold that will be experienced in order for an action potential to be triggered. That threshold is between -50 and -55 millivolts. In the rising phase of the action potential, we have the depolarization or the positive influx. And then in the repolarization or falling phase, that's the negative state being restored within the cell. There is a hyperpolarization that occurs, which results in a refractory period, and I will go in depth for that a couple of slides for now. Before I begin going into the depolarization and repolarization, I just want to review this threshold here. So when a neuron experiences a stimulus, there has to be a threshold met in order for this action potential to be triggered, like I discussed earlier. A great analogy for this is imagine you're trying to start a lawnmower. You're pulling on the cord, but if you don't have enough strength, nothing is really going to happen to the motor. Again, you're going to have to pull to a certain amount or certain strength in order for the motor to turn over and for the lawnmower to function. We can imagine the threshold as that. Anything, that increases the resting potential below this threshold is not really going to trigger an action potential. So the rising phase or the depolarization is displayed here. A stimulus or electrical change occurs, causing voltage-gated sodium channels to open, and sodium ions flood into the cell. Again, we have to remember that sodium ions are positive. And so we're taking this natural resting state inside of this cell, which is negative, and increasing the polarity by adding this influx of sodium cells as seen here. Again, I just want to reiterate here that in the resting phase, we're going to have a negative atmosphere within the cell, as seen here. And then once we have a stimulus, it's going to open the sodium channel, and we're going to have a large influx of sodium ions. This is going to increase the polarity within the cell itself, and this is causing a depolarization. Again, this is a positive charge or positive atmosphere within the cell. In the falling phase, repolarization occurs within a millisecond of the depolarization phase when the sodium channel closes and the voltage-gated potassium channel then opens. This allows potassium ions to leave the cell, which restores the cell to its negative state. Once the potassium has left the cell, the potassium channel closes immediately. It's a very quick function for that. Again, prior to this, we've got a positive atmosphere because of the sodium influx into the cell. Now the sodium channels have closed, and in result, potassium channels have opened, allowing potassium to leave the inner atmosphere of the cell. This is done in the attempt to restore the polarity to -70 millivolts. However, I discussed earlier that there is a refractory period. So a refractory period means that there was a hyperpolarization. So usually when the potassium channel opens and potassium leaves the cell, that can be done, too eagerly, so to speak, and have too many potassium ions leave the cell, making it too negative. This makes it very difficult for it to come to the resting phase again and have the potential to be firing another action potential. So there's a delay here between another signal. What we do in order to restore proper resting membrane potential is you're going to see a sodium-potassium pump within the membrane. The sodium-potassium pump shuttles sodium ions out and potassium ions in order to re-establish the resting potential. This is seen as a 3 sodium out and 2 potassium in with the pump. As we see here, we're going to have ATP, which is going to bind to the sodium-potassium pump. We have the 3 sodium being shuttled out and the 2 potassium being brought in, which of course is going to keep a phosphate here, and ADP is released. All right, to summarize, I am aware that that was a lot. It's a fairly straightforward process when you break it down into the steps. You have a cell which is going to have a normal membrane potential or resting potential at -70 millivolts. Something has stimulated this cell and has met the threshold, which is -55 millivolts. This causes the rising phase, which is the depolarization of the cell. When that happens, we're going to have the sodium channels open, and positive sodium ions are going to flood into the neuron now. This causes the inner atmosphere of the cell to be positive, which it really doesn't like because, again, the resting phase is -70 millivolts. So very quickly here, we're going to try to reestablish some normalcy with the falling phase or the repolarization of the cell. This is done by shutting our voltage-gated sodium channels to no longer allow excess sodium to enter the cell, and instead we're going to try to shuttle some of that potassium out of the cell to try to reestablish a resting potential. This is done by opening the voltage-gated potassium channels and allowing potassium to exit the cell. We can see that in this graph here. However, the potassium is a little slower to close its channel and can cause a hyperpolarization because of that. The hyperpolarization makes it difficult for another signal to be fired rapidly. So there's a bit of a delay there. In order for that delay to be closed or that resting potential to be met, the cell has sodium potassium pumps within its membrane as well, in addition to the sodium channel and potassium channel. ATP is going to bond to the pump, allowing 3 sodium ions out of the cell and 2 potassium ions into the cell. It's just a little plug and chug, you know. It's like drinking water. You're going to drink water and you're going to pee out excess. It doesn't stay in your body forever. It's the same with this. So what happens to the action potential once it's occurred? Where does that energy go? Where do these ions go once they're in the cell? So the sodium ions will diffuse to nearby areas, causing the membrane ahead of this action potential to experience a slight change in polarity. This is important because this change in polarity is going to prompt the voltage-gated sodium channels to open, which starts the process over. So it's simply further down the membrane. It's kind of like a wave, or if you think about shaking out a rug or a blanket, it travels along the edge of the membrane, transferring that message of the stimulus from one end of the neuron to the other.